Hello everyone, my name is Houssam. I'm working for Airthium company. I'm also a member of LGLL laboratory. I will present to you my work about the development of an algorithm to treat contact mechanics between bodies using FreeFEM, and this algorithm must be symmetric. I will explain later what I mean by symmetric. First, let's start with some basics. We will take a body omega in its initial configuration. If we apply a force at omega, therefore it will become phi omega. Phi represents the deformation. And if we take big X, a material point at omega, it will become small x. And the displacement field will be small x, the actual position, minus big X. And this displacement field will be our unknown in the following. We have two kind of problems. First, the linear elasticity, where we suppose that we have small deformations. Therefore, we don't distinguish between omega and phi omega, the initial and the actual configuration. And we have finite deformation, where we have large deformations, and we distinguish between omega and phi omega. In addition to the balance equations, for example, here sigma will denote the Cauchy stress tensor, and P, the first Piola-Kirchhoff stress tensor. We have boundary conditions. For example, here at gamma 0, we can impose a displacement, and on gamma 1, we can apply a load surface. Our displacement field is also a solution of the minimization of the total potential energy E over the set V, the admissible set, where here we impose a Dirichlet condition on gamma 0. In the case of linear elasticity, we have a constitutive law which describes the behavior of the material. Also, always in the case of linear elasticity, our total potential energy can be written in this form: 1/2 AVV minus FV, where A is a bilinear application, continuous, coercive, and F is a linear application and continuous, and therefore we can prove the existence and the uniqueness of the solution. In the case of finite deformation, and more specifically for hyperelastic materials, our total potential energy can be written in the form of an integral over omega of psi. Psi is the strain energy function minus FV, the potential energy of the forces. With some properties on psi, John Ball proved the existence of a solution of this kind of problem. Now, Signorini contact problem is a contact between a body and a rigid foundation. Here, our problem is nonlinear. We don't know actually the real contact area, but for example, if we denote gamma C is the potential contact area in the initial configuration, and phi gamma C its deformation. Therefore, we suppose that our real contact area is included in phi gamma C. The displacement field also is a solution of the minimization of the total potential energy over the set K. K is a set and will represent the non-penetration condition between the body and the rigid foundation. We have, for example, an example for a non-penetration condition. For example, if we take the actual position X on phi gamma C and its projection Y, therefore the non-penetration condition will be X minus Y scalar, the normal vector N, must be always greater or equal 0. For example, at the real contact area, this quantity X minus Y scalar N will be equal to 0. We can also write this problem in the form of a variational inequality, and using the properties of A and F, we will prove the existence of a solution Because K also is a convex and closed in a convex set. And in the case of linear elasticity, you can prove the existence and the uniqueness of the solution using Stampascia's theorem. Now, for the contact between two bodies, we will take the first one is the omega and the second one the omega 2. Here, the displacement are unknown as the displacement field for the two bodies, and is also a solution of a minimization problem of the total potential energy of the first and the second body with a non-penetration condition. Here we will take the first one as a slave and the second one as master. It means that our non-penetration condition will be as follows. We will take for each x1 at gamma c1 the potential contact area at the deformation. For each x1, we will have x bar its projection on the second body, and x1 minus x bar scalar n must be greater or equal 0. For example, if we switch the role and we take the second body is the slave and the first one is the master, therefore we will not obtain the same results when we use the finite element discretization. And therefore this formulation is non-symmetric. But for example, the user can choose the first body as slave. For example, if this first body has the finest mesh or is less stiffer than the second, but what if the first one has the finest mesh and is more stiffer than the second body? Therefore, we can see the difficulty in choosing between the slave and the master bodies. And also this issue occurs also in the case of contact between more than two bodies, or in the case of self-contact. Hence the need to create a symmetric algorithm in order to treat this issue. First, for the first method, I will use a penalty method in order to transform our constrained minimization problem into an unconstrained one. For example, here we will use a penalty functional p in order to penalize our penetration. For example, here in the case of linear elasticity, we'll minimize a energy 1/2 AVV minus FV plus a penalty factor, which has to be big, multiplied by the penalty functional PV, and PV, for example, here an example of a penalty functional. The role of this penalty functional in the case of penetration will be strictly positive. Therefore, if we multiply it by the penalty factor, which is big, therefore we will have a very big energy here, and the minimization problem will avoid the solution when this quantity mu multiplied by p is very big. And we have here, for example, for the eta the function, we have here an example has to be C2, because if you use a Newton method in order to compute the Hessian and in order to not obtain a problem with the computation, of course, of the Hessian matrix. And now we will apply our penalty method in the case of the contact of two bodies. For example, here we will consider our first body as the slave and the second one as the master. Therefore, we will write our first non-penetration condition by considering the first one is the slave and the second one is the master. And after, we will consider the second one is the slave and the first one is the master, and we will write our additional non-penetration condition And we will use two penalty functionals in order to penalize the penetration when we consider the first one is a slave and the second one is a master, and another penalty functional P2 in order to penalize the penetration when we consider the second one is a slave and the first one is a master. Therefore, our problem will be a minimization of the total potential energy plus the penalty factor mu times our first penalty functional and our second penalty functional. Therefore, now we have a symmetric formulation. We don't distinguish between the slave and the master body. Now we have another method in order to create a symmetric algorithm. For example, here at first we will take the first one, omega 1, as a slave and the second one as a master. Gamma C1 is the potential contact area in the initial configuration, and also gamma C2 is for the second body. And therefore, instead of using our non-penetration condition or function for each x1 at the contact potential area of the first body, we will have a weak non-penetration condition, and therefore we will obtain a minimization problem of the total potential energy with NC1 constraints. Here NC1 is a number of the nodes at gamma C1, and the phi I is the shape function at each node of gamma 1C or gamma C1. And therefore here we have a minimization problem with NC1 constraints. Here the constraints are written in a weak form. And yes, this formulation, of course, is not symmetric. And for example, if we simply consider after the second one is a slave and the first one is a master, and if we write our additional constraints here in C2 and C2 constraints, we'll have a minimization problem of the energy with NC1 plus NC2 constraints. But here in this problem, for example, we may have a numerical difficulty. Why? Because if we compute the Jacobian matrix of the constraints here, we may have row vectors that are linearly dependent, and therefore our matrix when we will use the Newton method will be singular. Therefore, we will obtain a numerical difficulty. In order to avoid this problem, we will use the interior point method. For example, here our problem will be written in this general form. For example, here we minimize the energy, and U is the degrees of freedom of the displacement field of the two bodies, and here Cu will represent non-penetration condition, and here C is a vector of NC1 plus NC2 components, and the inequality here, Cu greater or equal 0, is the inequality between each component of the two vectors. And we will use the slack variables in order to transform this inequality, the inequality constraints, into an equality one. And we will use the barrier, we will transform our problem into a barrier one in order to take into account the lower bound of the slack variables. And as our problem is a minimization, therefore we will use a descent method plus a line search method in order to find our solution, and we will use the Newton methods in order to find our descent direction. When we use the Newton methods in order to find our descent direction, we will find in our linear system a matrix of this form, where A denotes the Jacobian of the constraints, and A is a full row rank, because we introduce the slack variables, and G, in the case of, for example, in the case of linear elasticity, G is positive defined in the null space of A. Therefore, this matrix A, K will be non-singular. Therefore, we will not have a numerical problem, and our constraints are always linear, and therefore are qualified for the KKT condition. And also, we have the descent properties. Now I will describe briefly our contact algorithm. Here we use the fixed point method in order to transform our contact problem into a sequence of a minimization problem with linear constraints. For example, here we will use the previous iteration in order to find for each integration point XS on the contact area of the first body. We will use the previous iteration in order to find the closest segment of the second body to XS, and also we will compute the position of X bar, the projection of XS on the second body. We'll use the previous iteration in order to compute the position of X bar on the closest segment of XS, and we will use these quantities in order to we will use it in the actual iteration n, and therefore our non-penetration condition will be XS minus X bar scalar n. And because XS depends linearly on the degrees of freedom on the first body, and X bar depends linearly on the degrees of freedom of the second body, we will have linear constraints. And we can use, for example, for each iteration, we can use the penalty method or the weak formulation plus the interior point method. And the algorithm converges if the error between two successive displacement is small enough. Otherwise, for example, if we are in the case of Signorini's contact problem, and if our rigid foundation can be described by a C2 function, for example, we can use the cubic spline. We have this very simple algorithm, and which doesn't use a fixed point algorithm. And now I'll present some numerical validations. All examples was done by using FreeFEM and also by using IP-opt, the software IP-opt or the method IP-opt. Here we have a compression between two elastic blocks. Here we impose a downward vertical displacement on the top of the first body in order to make contact between the two bodies. Here we don't see an horizontal displacement because the Gaussian ratio is equal to 0, and the goal of this problem is to ensure that the pressure is transferred through the contact area to the second body. And here on the right figure, we can see a constant pressure. Here we are in the case of large deformations. Here we have two Neo-Hookean materials. We impose on the first body a vertical displacement, and after a horizontal displacement, as we can see. And this study is done, the quasi-static study. Also, we treated the dynamic case by considering the inertia of the two bodies. And this body is 10 times more stiffer than the second. Also, here we have another example where we impose on the outer border of this big disk, the outer border of this big disk is fixed. And we impose a vertical displacement on the small one, and the materials are Neo-Hookeans. That's all, and thank you.